A very good morning. So let us continue with the session of singly linked list. So welcome to the session. Before directly going to session, let us see the aim of the session. So to understand the concept of singly linked list, its purpose and implementation in C programming language, the instructional objectives like understanding the concepts, implementing a singly linked list using structures, performing common operations such as insertions, deletions and various traversals, and to solve the problems and write programs in singly linked list. So these are learning outcomes. The student will be able to understand the concept of singly linked list and its advantages, implement a singly linked list successfully using structures in C. Right, yes. So basically a singly let us go with the linked list definition. So it's basically a linear data structure consisting of series of connected nodes. So why is it basically used? To manage memory efficiently. So as I said, it is a collection of nodes. So a node in the linked list basically contains two parts. The first part is the data part and the second part is the address part. So and the most advantageous part is a node is created dynamically, that is at the runtime. So here no need to define its size at the time of declaration. So all of us know that this memory is a very important resource. So this memory is usually allocated during compile time. So what is the disadvantage of that? Once we allocate the memory during compile time, the memory allocation is actually frozen. You cannot increase the memory. No, so that is what is the problem. So here this is eliminated in our linked list because the memory is allocated at runtime. So this is the point that is to be remembered. So it is becoming more flexible, right? So now what are the different types of linked list? Yes, so we have singly linked list, we have doubly linked list, we have circularly linked list, circular singly and then circular doubly. So the only circular word means that it is circular, singly circular linked list, right? So anyway, according to our syllabus, constrained to our syllabus, we are going with a singly linked list. So just look at the singly linked list. So these are just the pictures just to analyze. So as the name says, singly linked list. So how many links? Only one link. So you can see that between the green color ones are the nodes. So if you see that, so you are having only one link, and that is also what link? It is the forward link. That is going to be the forward link. So that is why we are having two forward links. So there are three nodes, right? And just look at the second picture, that is the doubly linked list. You can see one arrow towards the forward and one arrow at the backward direction. So now here we are having how many links? Two links, forward link and backward link. So this is our doubly linked list, right? So now, so the third one and the last one is the circularly linked list. If you could see this, so if you see the previous slide, you can see what is there in the last node. Address part of the last node is null. You could see that, right? Null. So now here, but you see that in circularly linked list there is no concept of null. So what is happening? The last node is getting connected to the first node, right? So the last node is getting connected to the first node. That is why it is called as circularly linked list, and there is no concept of null, right? So according to our syllabus today, so we are going to implement our linear data structure, especially the singly linked list. So I am going to focus mainly on these topics, a brief introduction about SLL. So singly linked list, in short we call it as SLL, and what are the various operations that we are going to see? We are going to see the insertion, deletion, display and search operations. And yes, of course, why we are going to the singly linked list? As I said, it is going to be memory is going to be allocated at runtime. So we have the flexibility of declaration of memory or allocation of memory at the runtime. So we need not prefix it. So that is why, but that is what is happening in our arrays, right? So arrays, the memory is static. Okay, so static means compile time. So it is happening at static memory allocation is happening, and we don't want to use that because at times we are not very sure about the size of the data, that how much amount of data are we going to supply to our program. So in those cases we are going to see our SLL, right? And finally we are going to see certain merits and demerits. Yes, of course. So introduction to SLL, as you see this, so basically it is a linear data structure which is used to create, store and manipulate data efficiently. What do I mean by manipulating data efficiently? So that is what, as I said, whenever I am having whenever I'm having some amount of data, if I'm using arrays, say for example, so this slide needs some more explanation. So now, yes, so now this is an array, so with an address 0, 1 and 2. So now I can store 3 elements, so this is an array, right? But now suppose, now how many elements can I store here? So if I store say 2, 4 and 6, so now I am having 2, 4 and 6. I am storing 3 elements here. Is it possible to store the 4th element? Yes ma, is it possible to store the 4th element? It is possible once I try to erase some of the, either I have to delete one element and then insert the element, right? So now there is no place for the 4th element to be stored there, right? Now if I take an singly linked list, so now please keep this in mind, I am unable to store the 4th element here. So just keep this in mind. I am going to solve this problem, that is I am going to successfully store the 4th element in a singly linked list. Okay, so now I'm going to again focus back on my singly linked list. Yes, so basically it is a collection of nodes. Your node, exactly to picturize in the memory, your node looks like this. So collection of node, as I said, every node contains 2 parts here. As you can see, the first part is the data part and the second part is the address part. So now here 10 is the data and null is the address, that is it is the only single node which is available. I hope you are clear with this, right? So and just keep in mind this particular problem, I am having an array of size 3, I am storing 2, 4, 6, 3 numbers. I want to store the 4th number, but now due to lack of space, it is not possible for me to store, and I am going to solve this problem in singly linked list, right? Yes, so now this is a sample representation of a singly linked list. This slide also requires some attention. Just look at this slide. So now the first thing, all the green colored ones are the nodes, right? And now, so all the green color one are the nodes, and as I said, every node has 2 parts, the data part and the address part, right? So now 5 and 5 is having the address of next node. So just what is the next node? Data 6. What is the address of 6? 200. That is why 200 is stored in the first node. What is the next node address? 300. So 300 is stored in which part? Address of 6. Am I right or not? It is stored in the address part of 6. So totally there are 3 nodes. What is the next of 7? What is the next node of 7? There is no node next to the node with data 7. That is why it is marked as null, right? So now what is the starting point? What is the starting point? The starting point is node 5, and what is the address of that node 5? 100. That is why that 100 is stored in which part? Head. So this, you can just imagine something like a train where the first one will be the engine, next to engine all the bogies will be there, and in the last we will be having the guard, right? So now in the last and after the guard, obviously we will not have any coaches. So this is exactly the same way, and every node will have one forward link to the next node except the last node, where the last node next value will be as null. Okay, that will be set as null because there is no other node. So this is going to store the addresses. So this is a typical singly linked list. As you can see, there is only one link to the forward, right? I hope you are clear with this. And why is this 100 stored? The address of the first node. The address of the first node is stored in the head. Head is basically like a pointer, and you know what is a pointer? It is a variable that stores the address of another variable or something, right? So now that is why head is a pointer. So we will be storing the address of the first node, right? And while implementing this, yes, I just want you to have a look at this. So this is the node structure definition where we store. So how do we store? As I said, how many data you are storing? You are storing the data part and you are storing the address part. So now int data struct node star next. So now what is that? So star next. So the moment the compiler sees star, it understands that it is a pointer, no pointer. So pointer means what? It's storing the address. It is storing address of what? Next node. Am I right or not? It is storing the address of next node. And what is a node? What is the data type of node? Struct. So that is why struct node star next. Of course, something like your self-referential structures, right? And then the next one is, as I said, struct node star head. So the head is basically a pointer which is again storing the address. So this statement holds true. So this particular statement holds true when there are no nodes, when there are actually no nodes, then head value will be definitely equal to null. So this is our basic node structure definition which we will be implementing in our C programming, right? So now just look at the singly linked list picture. I hope you are clear with this. There are 3 nodes, the data parts are 5, 6 and 7. The address parts of the next nodes, you can see what is the address part, and always I will be referring it with the head. So head will be pointing to the first nodes. Okay, so now I hope you are clear with this. Yes, now what are the basic operations that we can see? Okay, so in the starting we will be having many terms, but then when we go in a flow, these terms will become very familiar to us, so we will be feeling very easier to understand. So now what are the basic operations? Of course, we can insert a node, we can delete a node, we can search and we can display. So now the insertion part. So let us focus only on the insertion. Insertion is what? Already the nodes are existing. I am trying to insert a particular new node. I am going to insert a new node. Yes. So now see, for example, so now yes, let us get the same way. So now this is a sample list. So I am going to store, right? So I am going to store. So this is a, say for example, this is again a list which is available, right? This is a list which is available. So now here, yes, now I want to store a new node. Now in which position can I store? I can store this, I can attach this node, I can attach this particular node, okay, as the first node. So of course here I will be having the head here. So now yes, so I can attach this in the first position, I can attach it in the last position, or I can attach it somewhere between these two or between these two. Am I right or not? So that is why, so now here what is there? So that is why, see the insertion, again it is divided into 3 parts: insertion in the beginning, insertion in a position, specified position, and insertion in the end. Am I right or not? Yes. So now let us continue. Insert a node in the beginning. So I want to see everything here as far as possible. I have tried to explain it only with the help of diagram. Yes. So now, yes, now insertion of a node in the beginning. Am I right? Yes. So now see, I want to insert a node. Say for example, yes, this is the existing thing, and so what is the existing linked list? 5, 6, 7 are the existing linked list. So address of the head, address of the first node 100 is stored there. Yes. Now I want to insert this new node, right? I want to insert this new node. So first I have to create this new node and I have to insert it in the first. Am I right or not? Yes. So now tell me, when I have to insert it in the first, which means what? It has to come in this position. So it has to come in this position. Am I right or not? So this node 2 has to come here, and what is there next of 2? This null. Am I right or not? So actually it is like this. So this null has to be removed and it has to be connected with this. Am I right? Yes. Now is this enough? No, because head is pointing to which node? Now second node, but head has to point to which node? First node. So I have to make one more connection. So this is the first connection that I have to make. This is the first connection and this is the second connection I have to make. Am I right or not? Yes. So now let us look at the algorithm, because if we know the sequence of steps, we can definitely convert it into a program. So now the logic is very important. So the generalized logic is being put up in the algorithm. So what is our main mission here? Insertion of a node in the beginning. So after insertion of the node, can you see here, after insertion of the node, now in the earlier picture what was there? 5 was there. Am I right or not? So in the earlier picture 5 is the first node, and now if you see here, so 2 has become the first node. Next of 2 was null. So this was null. This null is removed and it is replaced with the address of 5, which is 100, and now 2 becomes the first node. What is the address of 2? 600. So 600 is replaced in the head. This purple one is the head. Am I right? So this is the insertion of the node in the beginning as the first node, right? So now here, so that is what is the pictorial representation. Yes, now this is the insertion algorithm, insertion in the beginning. So first, as I said, you have to create a new node with a given value, right? So create a new node, so you have to use an malloc function, dynamic memory allocation function. It is also called as dynamic memory allocation function. So use an malloc function and first create the node, okay, and then check whether the list is empty. How we will know whether the list is empty? If head is equal to null. So if head is equal to null, then directly, suppose, see, now here head is equal to null. So now here if head is there and which is equal to null, so this is my new node, right? So this is my new node here. So what will I do? Just this new node address is that I will update it in the head. yes, this new node address, it will be updated in the head. So new node of next is equal to null, right? So if the new node of next is equal to null and head is equal to new node, I just attach that to the new node. And what is the previous one? Suppose if head is not empty, that is my previous case, right? So that is my previous case when head was not equal to empty. So now what did I do? New node of next is equal to head. So that is this link, new node of next. So this new node of next is equal to head. That is what is happening here. So here if I am having to new node of next is equal to head and head is equal to new, and head is equal to new, that is what has happened here, right? So and head is equal to new node. So this is my insertion in the beginning, right? So I hope you are understanding. So these are the sequence of steps. This is the main logic that we have to use in order to insert a node in the beginning, right? So now insertion at the end. Yes, now one thing I want to let you know. So yes, I think yes. So before going with this, right, so insertion in the end. Now here what is happening? So again, analyze the same thing with the help of a diagram, you will get an idea. One thing you have to understand, there are no names for any of the nodes. Yes, there are no names for any of the nodes, only the node which I am creating, that is to be inserted, only that is having what name? New node, that is having the name as new node, but here absolutely no name. So how do we identify? We identify the first node with terms of head, we identify the last node as last node of next is equal to null. Are you understanding, ma? So it is the most important concept that has to be done is the first node will always be identified as it is attached to the head pointer, and the last node's next, whatever may be the last node, that last node's last node of next will be equal to null. So that is what is the identification point. Other than that, I don't have any identification point here. Now I want to insert the node at the last. I want to insert the node at the last. How do I identify that? So, and I cannot move the head. Please do not, it is never a good programming practice to move the head. We should never move the head pointer. So I am creating a carbon copy of head pointer by telling this PTR. Okay, so whatever is the address of the head, so same thing I will be writing it as, say, PTR is equal to head, right? So now PTR is equal to head. So now what is that? I am creating a carbon copy. Now is PTR of next equal to null? No, because PTR of next is pointing to what? 200. Am I right or not? Yes. Now see here. So PTR of next, it is going to 200. So now again here PTR is there. So now my PTR is residing here, right? Now again, I don't know, right? So again I am checking, is PTR of next equal to null? No, because PTR of next is equal to 300 now. So PTR is equal to PTR of next. Again my PTR has moved here. So now again I am writing here PTR. So now see here. So now PTR, now what happens? Now tell me what is PTR of next? PTR of next is equal to null. Yes, what is PTR of next? Now PTR is pointing to the last node. So obviously PTR of next is equal to null. PTR of next is equal to null. Yes. So now what is happening? Yes, so I have reached the last node and this is to be attached node. See here, the yellow ones is to be attached to the green family. So now there are 3 nodes in the green family. To be attached node is what, ma? 11 with a value null, right? So that is the value to be attached here. So now tell me what I have to do to attach here. So this null is there, no? This null, this has to be replaced and we have to just attach this, right? So what is the name of this node? What is the name of this node? PTR. And what is the name of the node which we have newly created? It is new node. So now tell me the name of this particular link, PTR. If this is PTR, this is PTR of next. So PTR of next is equal to new node. PTR of next is equal to new node. Am I right or not? So we have to attach this particular link. That link also I will show you here, right? So that link also we will show you here. So now see here. Yes. So now if you see this, yes, so now after attaching, so now this 11 also has come to the green family, it is already attached. So can you see this? And I have put up this particular link, right? So PTR. So what is this particular link? This particular link is nothing but PTR of next is equal to new node. This is PTR of next is equal to new node. Just as a sample I have written. Yes. So now the same thing. So here what is this, ma? You have to go to the last node. So of course, see, first thing is create a node with a given value. Yes, the first 3 will be same. So check whether the list is empty. How will you check the list is empty? If head is equal to null. If head is empty, directly attach it to the new node. If head is not empty, then what is that? you first define another node and say PTR, right, and then initialize it with the head, and keep moving the PTR until we reach the last node, and then PTR of next is equal to null, and finally set PTR of next is equal to new node. So finally set PTR of next is equal to new node. So that is what is insertion in the end, right. Now, so now we have inserted node in the end position, we have inserted in the first position, and now what is that one? This is insertion in the specified position. So insertion in the specified position is nothing but we have to set a basic pointer. So now basically if this is the list here, okay, so now what we have to do when we are I want to attach this in the middle, right. So now I want to attach after the second node, I want to attach it as the third node. So now what I have to do, I have to attach with two different links. Yes, so first I have to move, if I want to attach it at position 3, how many nodes I have to move? I have to move 2 nodes. So I have to move node number 1, then I have to go to node number 2. Here I have to stop, and here is my new node. So here is my new node. So then I have to make use of this particular new node and insert the node in a specified position, right. So see this diagrammatically, if you see here, it will be easier for us to understand. So now what is happening here? So this is our existing list. I want to insert again 7, right. I want to insert 7 here. So I have the name only for the new node 7. I have the name only for the new node 7. So I have to insert at which position? Position is equal to 3. Position is equal to 3. So how many nodes I have to move? I have to move 3 minus 1, which is equal to 2. So if whatever is the position, I have to move n minus 1 positions. So since I have to move in the third position, so I will start my PTR with the first one. So now again I will take the position, again I will go to the second. So see here, PTR is stopping here, right. So how do I conclude? PTR of next is equal to new node, and new node of next is equal to PTR of next. New node of next is equal to PTR of next. Here I would like to give you one suggestion. So wherever emphasis needs to be given, I am going to tell that. So generally students will think, okay, we have to break this link and we have to just attach it. If you break this link, you will, this node number 7, this one will start flying in the air. So always remember, first we have to make the back connection. That is, what is this connection? New node of next is equal to PTR of next. The name of this node is PTR. The name of this node is new node. So what is this back connection? New node of next is equal to PTR of next, right. So now this is new node. So this one is new node of next is equal to PTR of next. So first make this connection, then we can write PTR of next is equal to new node. Right. So how many connections we have to make? 2 connections. One is the back connection and next is the front connection. First, which connection you have to make? We have to make the back connection. What is that connection? New node of next is equal to PTR of next, and then PTR of next is finally connected to the new node. Yes. So if you could see this, yes. So now the same thing is happening here. So if you see, yes. So now see here. So that is what is happening. So that is what I have given in this, okay, in the specified position. Okay. So now here, so new node of next, see the step number 6, all the first ones are the same. So see the step number 6, new node of next is equal to PTR of next, and PTR of next is equal to new node. So just be careful with that last node. So, and remember, always we have to make the back connection first and then break the original connection, right. So now displaying the elements in a singly linked list. Of course, this is also very simple. So if the list is empty, step number 1, if the head is null, then the list is empty, no elements to display. What is the second node? So here what is happening? Head is not empty. Then what is happening? You will define a PTR. Go to the next, display the data. Again go to the next, display the data. So once finally PTR comes to the next, PTR of next is not equal, PTR of next is equal to null here. So I will stop. So now here the same thing. So we will start from PTR is equal to head, right. So we will start from PTR is equal to head. So now here, so once we initialize PTR is equal to head, and we will go to the next nodes until PTR of next is not equal to null. So now here we are going to display the data, again we are going to display the data, and finally we are going to come out as it is reached the null point. So these are the steps which are available in this. Right. So always we are checking, as the first part we are always checking if head is equal to null, that's it, right. So this is the display operation. So once you know the insertion operation and moving to the next nodes, the display operation becomes quite simple. It becomes very simple. Obviously our starting point always will be head, right. So like that we will be going. Yes, now to search for a particular element, that is also the same case. If you see here, if the linked list is empty, then if head is null, okay, then there is nothing to search, right. But if it is not empty, and if you want to then you are asking the user input the data to be searched, say x, okay, so int x. Now I am defining a pointer, and again I have to go through the entire list and see whether that data is equal to x. Am I right or not? Now see, for example, in this list I want to say search for, say, data 7, okay, so I want to search for data equal to 7. So now I am writing x is equal to 7. So now I have to search. What is my starting point? PTR is equal to head, so I will start from head. So now here, what is PTR of data? What is the data of PTR? So now see, for example, now PTR of data. What is PTR of data? PTR of data in this case is equal to 5. Is 5 equal to 7? No. Right. So now what will I do? PTR is equal to PTR of next. So now see here, what am I doing? PTR is equal to PTR of next. Like that it migrates. Am I right or not? So again it comes here. So PTR of data 6. 6 is equal to 7? No. Now again it comes to next. Yes. Now here see. Now what is there? PTR of data. So now PTR is pointing to this. Am I right? Now PTR is pointing to this. What is PTR of data? 7. So now, and what is x? 7. So now you see that PTR of data is equal to x. 7 is double equal to 7. Am I right or not? Yes. So in this case, so I have started from head. Everywhere I am just seeing whether it is the value is equal to 7 or not, and I am going on comparing, and I have come back. Am I right or not? So now you see, what is happening. PTR has come here. I have compared the value, and now it says yes, the element is found. So I need not go till the last node. Okay, so in this picture only last node is one node available, but maybe there are more nodes available. So since here I am seeing that the data is available, I have just stopped the operation and I just print a message that element is found. So we have started from the head pointer here, and then we have come to the and then we have come to search the element 7, and we have printed the value, right. So this is our search operation. Since we are moving from the head to the last, it is also called as linear search, or also term it as sequential search. Now finally the deletion. So I have come to the deletion operation. Again I can delete an element from the beginning, I can delete at a specified position or delete at the end. So deletion from the beginning. So before I scroll with this, yes, now see here, for example, so now see, this is this one case, okay. Now case 1, how many nodes are available? Only one node, right. So 7. Now if I delete this 7, are there any nodes available? No nodes available. So now what should happen to head? Head should become null. Head should become null. That is what is my first case. What have I written here? When I am deleting the node at the beginning only, but now there is only one node available, right. So when only one node is present, and this node also I am deleting, so this 100 will become invalid because this node is getting deleted. So now what is happening? Once I delete this, after successful deletion, you can see here, after successful deletion, head becomes null. Am I right or not? So this is deletion from the beginning. Suppose this is not the case, okay. Why, ma'am, only one node? Okay, let us think. So now see, deletion from the beginning, when there are more than one node, when more than one node is present. Yes, now I don't know whether 3, 4 or 5, but there are some nodes present now. So now what happens here? So generally speaking, okay, so when I want to delete this, so I see that, so head of next is not equal to null. So simply tell me what we have to do. Now I have to delete the first node. So I am just encircling like a cloud. So this has to get deleted. So when this is getting deleted, what will happen? The head has to be updated with which value? The head has to be updated with, instead of 100, head value becomes 200. Now head value becomes 200, as that is the first node now, because this is going to get deleted. So yes, so now that is what. So now here after successful deletion, okay, after successful deletion, what has to happen? This node will no longer be available here. So this will be pointed to head, and yes, of course, this value will be updated with 200. So this is our deletion from the beginning. Even in this, we have seen two cases, when there is only one node and when there are more than one node which is present. Right. So now, so this one is deletion from the beginning. Yes, so if you see this, yes, and deletion from the specified position. So deletion from the specified position is, suppose I want to delete it from say middle, second node or third node or whatever it is, right? So when I am deleting this, okay, so always have to keep track of a previous node, always have to keep track of a previous node, because in SLL, if you come front, it is just like our life. When you come front, there is no U-turn, you cannot come back, there is no previous link, right? You cannot come back. So once you go to the front, it is not possible to look back and see the link. So we have lost that particular contact. So that is why whenever I am moving ahead in the forward direction, I am keeping the carbon copy. So now here first PTR was there here, and now when PTR moved here, before I moved PTR, I am having a PTR1 as its carbon copy. Am I right or not? So once I want to delete this, when I want to delete this, so now what will I write? PTR1 of list, okay, PTR1 of next is equal to PTR of next. So when this node is no longer being available, so what connection I have to make? The top one. Can you see the new link? So how will you make that new link? This is what is this box? This is PTR1, and this node doesn't have name, but it is what? PTR of next. This is PTR of next. So what will the name, what will be the name of this? PTR1 of next is equal to PTR of next. PTR1 of next is equal to PTR of next. This is PTR and PTR of next, that is this, right? So the same thing I have shown in the form of a specified position. So the same thing, deletion from a specified position, that is you have to go, you have always, we are starting from PTR is equal to head. So see, please see the step number 2. So now here we are seeing only that. So we will see with PTR of next is equal to head. So now we will start with head and we will start moving, and we will go to that up till that particular node, and that we will be trying to delete it, right? Now this is the last one, where deletion in the end. So always when we see this deletion in the end, always when we see the name as end, it is ending is nothing but the last. So as we know here, the last node. So what is the next pointer to the last node? It is going to be end. It is going to be null pointer. Am I right or not? It is going to be null. So the last node will not have any address, right? So that is our understanding. So always we will start with head. So if you see here, always again the same thing, I have my PTR equal to head and I move till last, but I will not cross till after 300. I will not cross, because what is happening in because 300 next value is equal to null. Am I right or not? So your PTR finally comes and stops here, and as I said, every time I move PTR, I have to make this as PTR1. Am I right or not? So when this was PTR, this was PTR1. When this is PTR, this is PTR1. So now what is my agenda? I have to now free this PTR. So when this is no longer available, you tell me what I have to do. This 300, is it valid? No, because when this node itself is deleted, this value 300 will not make an impact. It will give you some, now it becomes an irrelevant value to my program. So now I have to make this as null. What is the name of this node? It is PTR1. So now I will make it as PTR1 of next is equal to null. So after this particular deletion, what will happen? The same thing, I am having this head as 100, and I am having this as 5 and so I am having this as 5 and 200 here, 5 and 200, and finally here I am having 6 and null. So after this I am making it as 6 and null. So this is my PTR null, and 7 is removed, which means I will write it as free of PTR, that is PTR is equal to this data. So whatever this data is there, this entire thing is lost. So after deletion, this is going to be the case, right? So that is what is so now if you could see this, I have already made the animation here. So if you could see this, yes, which is available. So once if you see PTR1, yes, so what is happening here, I have deleted this 7, and then PTR1 of next is equal to null. So this is the deletion algorithm, so using which, so that is what set, if you could see the step 6, right, set ptr1 of next is equal to null, and finally free the ptr, and the remaining steps always say that how to move that ptr. So starting we are having ptr is equal to head, and we are moving the ptr and ptr1 pointers next until we go to the last, and finally we will set the previous one, no. So if ptr is there, ptr1 of next should be equal to null, and finally we will free the ptr. I hope you are clear with this. So this is the deletion. So if you could see this, so as I said, so now the conclusion, so effective memory utilization. Now come back to the same problem. This is my array, so I am storing 2, 4 and 6. Now convert the same thing into a linked list. So I am just, so this is 2, this is 4, this is 6, right. So now I want to store some other elements, I want to store one more element here. Is it not possible? Definitely it is possible. Again what will I do is, I will again create a node, I will store 7 and I will attach this to the list. So in our childhood we would all have played that game, no, we are making toy train, toy vehicle, or something where we go on attach red, green, blue, how much ever we want we are going on attaching. So the same thing it is happening. So that is what is happening here also. So it is, so no need to decide the memory earlier, like exactly tell me how many elements you are going to use. I cannot predict in the starting situation, I cannot predict how many elements I require to use. So it depends upon the it dynamically depends. So that is what is the main thing here. So utilizing the memory effectively. So that is what the first thing is, and insertions and deletions can be done easily. So 2, 4, 6. So deletion. Now if I delete 4, so now what is happening here? Now 4 is not there, so again a gap, so you have to shift the 6 here, right. But here it is not happening like this. I want to delete 4, what can I do? So ptr of next, just attach this to this, that's all, just one link attachment. So it can be it can be very easily produced. So that is what is, first thing is utilizing the memory efficiently. The second thing is the insertions and deletions can be done properly, easily, and finally it can be applied where we exactly do not know how much amount of data is to be supplied to the program. So that is what is happening. Say for example in your house you are organizing a function, okay, say a birthday party you are organizing. Can you predict exactly the total number of people who are going to come? Definitely not possible, no. So if you invite 100 people, maybe 90 will turn up or 150 will turn up, okay. So the same way, so when we don't know the exact amount of data, okay, for that we can use the singly linked list, because the memory allocation is at runtime, dynamic memory allocation. So that is the only advantage of this. So here we have seen various operations. So any queries, you can just contact us. Thank you.